Good morning, one and all. By offering my humble pranams to Lotus feet of His Holiness Jagadguru Dr. Sri Shivaratri Rajendra Mahaswamiji Garavadu, and seeking the blessing of His Holiness Jagadguru Sri Shivaratri Deshikendra Mahaswamiji Garu. Myself, Amrita Varshini from Physics Department, welcome all of you to 2 days International Young Researchers Symposium 2025 on emerging trends in advanced material organized by Department of Physics, SJCE, JSS Mysuru. Let us commence this wonderful event by knocking the divine. I request Ms. Duti, a first year MSc Physics student, to present the invocation.
श्रीकणनाथ सिन्धुरावर्ण करुणसागर करिवदनालम्बोदर लक्ष्मीकरा अम्बासुत अमरविनुत लम्बोदर लक्ष्मीकरा सिद्धचारण गण सेवित सिद्धि विनायक ते नमो नमो लंबोदर लघुमिकरा अम्बासुत अमर विनोद लंबोदर लघुमिकरा सकल विद्या आदिपूजित सर्वोत्तम ते नमो नमो लंबोदर लघुमिकरा अम्बासुत अमर विनोद लंबोदर लघुमिकरा.
Thank you, Duti. Now I request Dr. Madhusi, Head of the Physics Department, to welcome the gathering.
Good morning, everyone. I submit my humble pronouns to the lotus feet of His Holiness Sri Shivaratri Deshikendra Mahaswamiji, and also seek the blessings of His Holiness Sri Deshikendra Rajendra Mahaswamiji. It's a great pleasure to welcome you all for this August gathering. First of all, I like to welcome our chief guest for this function, our teacher, Dr. Krishnavini Madam, Chairperson, Department of Studies and Physics at University of Mysore. I also like to welcome our Honorable Vice Chancellor, Dr. A.N. Santosh Kumar, for this function. Thank you for your guidance and the support, sir. I also like to welcome our principal, Dr. C. Nataraju sir, for this function. Thank you for your motivation and support. I also like to welcome our Dean Science, Dr. Madhu sir, for his leadership for the science departments and also for impact. welcome all the officers of our university, deans of different technology sciences and technology, and also all the heads of the departments, and all the students who have come here, who are the main focus of this main function. So with this, I'll just give a very brief introduction for this symposium. So as the name says, it is a young researchers symposium, mainly focusing the young researchers who are the main workforce of all the research which is happening throughout the world. So with this intention, we have planned this symposium, and we have received around 170 participations, and out of that we have 25 oral presentations. Um, Along with that, we have some 5 invited talks from different experts from different material science experts throughout the world. So this is our summary of our symposium. And why materials? Uh, Again, if you take any technology, the main driving force is the materials. So it may be in the field of technology, or it may be even in the field of life science. Main thing is material science. So most of the technology is driven by the materials. So it can be even sustainable energy like solar cells. So we still have a lot of challenge, especially we have only 25% of efficiency with the present solar cells. So there is a lot of efficiency, challenges. Even the same thing with respect to energy storage, or it can be even in the field of biosciences. So this is the main purpose why we have assembled here, and I'm very happy to tell you that our participants are from entire all the disciplines. We have from mechanical engineering, civil engineering, science, physics, maths, chemistry, biotech, and everyone. So this is one of the unique feature of this conference. So with this, I hope you will have insightful and joyful 2 days of stay here. So again, I will welcome you all, and thank you for being here.
Thank you, sir. Now I also welcome our beloved HOD, Dr. Madhu C, to this event. I request all the distinguished guests to inaugurate this event by lighting the lamp and offering floral tribute to His Holiness Mahaswami.
Yes, yeah. Sir. Yes, yeah.
Today we are honored to have with us the renowned researcher Dr. S. Krishnaveli, Professor and former Chairman of the Department of Studies in Physics, University of Mysore. Dr. Krishnaveli has completed MSc in Physics in 1997 with 82% securing first rank and winning 4 gold medals from University of Mysore. She completed PhD in Physics from University of Mysore in 2003 with CSIR Senior Research Fellowship. Professor Krishnaveli has published more than 85 research papers in reputed journals with high impact factor. Recently, she has published papers in Elsevier Nano Energy and Chemical Engineering Journal with impact factor of 18 and 13.5. She has also filed one patent regarding the triboelectric nanogenerator in 2024. She has presented more than 90 papers in national and international conferences. She has H-index of 16, ITAN index of 21, and total Google Scholar citations of 1,369. He has handled and handling several projects from national agencies like IUAC, UGC, DST, SED, and CSIR, etc. Recently, she got reputed project under DST Shore scheme to carry out research in biophysics field. Professor Krishnaveni has visited many countries on various capacities like Italy, Thailand, etc., on an invitation to deliver invited talks in the conferences. She is also serving in various capacities in universities of Mysore administration. She is a coordinator for intellectual property rights cells, chairperson for internal complaints committee, coordinator for Chinese exchange program, chairperson of physics BOS in KSOU, member of various BOS in different universities and college members in various committees of University of Mysore. Now I respectfully invite our chief guest, Professor S. Krishnaveni, to address the gathering.
Good morning, one and all. Dignitaries on the dais and off the dais, and mainly young researchers. So it is truly an honor to be here at the International Young Researchers Symposium on Emerging Trends in Advanced Materials. As we gather to discuss material science and technology transfer, we are not just exploring the frontiers of research, we are shaping the future of industries, economies, and society. Material science has always been a driving force behind human progress. From the iron and bronze that defined ancient civilizations to the advanced nanomaterials that fuel today's technological revolution. Materials have played a crucial role in shaping the way we live, work, and innovate. Today, we find ourselves at a crossroads where sustainability, health, and environmental responsibility are no longer optional, they are imperative. The challenges of climate change, energy security, and healthcare advancements demand solutions that are both scientifically robust and commercially viable. Such symposiums like this are crucial because they foster exchange of ideas between the researchers and industry leaders, ensuring the cutting edge discoveries do not remain confined to laboratories but make tangible impacts in the real world. The importance of material science extends beyond academia and industry. It is central to building a sustainable future. Whether it's developing next generation batteries for clean energy, creating biocompatible materials for advanced medical treatments, or engineering eco-friendly materials to mitigate environmental damage, every breakthrough in this field has the potential to transform lives. For example, sustainability and green technologies are at the forefront of global challenges. The world urgently needs sustainable materials to combat climate change, reduce waste, and improve energy efficiency. In this regard, breakthroughs in energy storage such as solid-state batteries and graphene supercapacitors are enabling more efficient renewable energy grids. Additionally, biodegradable and recyclable materials are replacing plastics, reducing environmental pollution and making a lasting impact on ecological balance. Advanced healthcare and biomaterials are revolutionizing the medical field. Smart biomaterials are transforming medical treatments from self-healing implants to drug delivery systems that target diseases at the cellular level. The emergence of 3D printed tissues and organs holds the potential to revolutionize regenerative medicine, offering new hope for patients in need of transplants. Furthermore, nanomedicine is allowing for precise cancer treatments with fewer side effects, enhancing both the effectiveness and safety of treatments. The future of computing is heavily dependent on new materials. Quantum dots for quantum computers and 2D materials like graphene for ultra-fast transistors are paving the way for next generation computing. Neuromorphic materials are aiding in the development of artificial intelligence systems that mimic the human brain, making computing more energy efficient and powerful. These advancements in material science are crucial in shaping the future of technology and artificial intelligence. Extreme conditions and aerospace innovations are also being driven by cutting edge materials research. Materials for space exploration, such as radiation resistant and self healing materials, are essential for interplanetary missions. Lightweight, high strength composites are reshaping aircraft and satellites designs for fuel efficiency and durability. Moreover, hypersonic materials which withstand extreme heat are key to future space travel and defense applications, opening new frontiers for exploration and security. Smart and functional materials are redefining industries. Self-healing materials can repair themselves, increasing durability and lifespan in construction, electronics, and vehicles. Metamaterials enable advancements in antennas, optical devices, and even invisibility cloaks, demonstrating the vast potential of engineered materials. Additionally, flexible electronics and wearable materials are revolutionizing personal devices and healthcare monitoring, making technology more adaptable and integrated into everyday life. Sustainability and environmental impact are another pressing concern. Some advanced materials rely on rare earth elements or hazardous processing methods that harm the environment. A shift towards green chemistry, biodegradable materials, and recycling technologies is essential to develop sustainable alternatives. Circular economy models can reduce waste and ensure the responsible use of resources, promoting environmental consciousness in materials research. Integration with existing technologies remains a complex issue. New materials often struggle with compatibility when integrating into current systems, such as semiconductor manufacturing or aerospace applications. Advanced computational modeling and AI-driven materials design can predict compatibility and speed up development cycles, making it easier for novel materials to be seamlessly adopted into real-world applications. Finally, the long research to application cycle often delays the real-world impact of material science breakthroughs. Translating lab discoveries into practical applications can take decades due to regulatory and testing constraints. Faster prototyping methods such as 3D printing of materials, high throughput experimentation, and digital twins for materials can significantly shorten development time and bring innovations to market more rapidly. As we engage in discussions over the coming sessions, let us remember that the knowledge shared here has the power to shape industries and define the future. Finally, to end my remarks, material science is the foundation for solving the biggest technological challenges of the 21st century, whether it's creating cleaner energy sources, revolutionizing medicine, enabling quantum computing, or supporting space exploration. The materials of today will define the technologies of tomorrow. I extend my sincere appreciation to the organizers, the distinguished speakers, and the bright young minds participating in these workshops. I look forward to insightful discussions that will not only push the boundaries of material science, but also pave the way for real world impact. Let us work together to turn today's ideas into tomorrow's solutions. Let me conclude with an inspiring thought. Innovation is seeing what everybody has seen and thinking what nobody has thought. And also another one, the best way to predict the future is to invent it. Thank you one and all the best.
Thank you, ma'am, for your insightful words about this symposium on emerging trends in advanced materials. I request our Honorable Vice Chancellor, Professor A.N. Santosh Kumar, to felicitate our esteemed guests and kindly invite all the dignitaries to join this gesture. We are honored to have with us the Honorable Vice Chancellor of JSSSTU, Professor A.N. Santosh Kumar. I kindly request him to present the presidential remarks for this event.
Very good namaskar. Very good morning to everyone present here. At the outset, I submit my most respectful pranam the lotus feet of His Holiness, Jagat Guru Sri Shivaratri Deshikandra Swamiji, and His Chief Divine Guests. Our chief guest of today's inaugural program, Professor Krishnaveni, Professor, Department of Studies in Physics, Master Gotri, Dr. C. Nataraju, Principal HJC, Dr. P. Mallu, Dean Science, Madhu Chandra, the person behind organizing this particular symposium, also the Earth Department of Physics, all the other coordinators from the Department of Physics who have taken a lot of effort and putting effort to organize this, deans and officers from the university, heads of the departments, all my other colleagues from different departments here for the inauguration, and also most important, the young minds, right, who are all young researchers, who are assembled here for participating. I'm extremely happy that almost 170, he said, are participating. It was a big number. We participating in this young researchers symposium. And I'm also happy because after a very long time, I'm seeing Department of Physics in the forefront of organizing a symposium for 2 days. Normally, other departments, congratulate the entire Department of Physics led by Dr. Muthu Chanbasappa organizing this. Our chief guest, has stated and also, highlighted the importance of materials, especially advanced materials, and how it can be, used, whether it is transportation systems or energy systems, clean energy, and, quantum computing and computing. These are things which I think the speakers are also going to speak over the next 2 days. I see some very big names also in this particular area. People coming from Poland, Indonesia, from IIT, and some of the very eminent people in this particular area are also like coming and delivering. Just I request each one of you to actively involve in this particular, engage in this particular involve and get maximum benefit out of this symposium. I will not take much time in talking about the emerging trends in advanced media. However, as the administrator, we do have the experience of running an engineering college for more than 60 years. We started university in 2016, 17, and we immediately recognized the importance of science programs. And we started started with chemistry, mathematics, and later on we have added several programs. In fact, the latest editions will be the MSc programs in semiconductor technology, MSc in electronics. So we have in almost all analytical chemistry. So many different programs that we are running in science because we have realized the importance of science. Unfortunately, many people, including parents and students, of late, not of late, from almost 2-3 decades now, slowly going away, moving away from science. This is very unfortunate. There cannot be any engineering and technology without science. Technology can tell you and help us solving real life problems. But without science, you can't solve any other problem, you can't build any technology. Because of advanced materials, miniaturization is possible today. A computer which was the size of this room, today has come very small where you can even hold it on your laptop or even your palm tops, etc. It is simply a testament to the fact that all this is possible because of the advances that we are making. There is a mad rush for everybody to go towards engineering and other programs. Subsequently, there is the emergence of BCA, the computer applications, and the CA. These programs are taking away and a lot of people. In fact, before coming here, I was talking to Professor. She's saying every year people come and get admitted and leave after a few days. They're not able to digest the fact. Where does this particular where is the problem this? First of all, right from school days, they should be enthused with proper the whole thing about science is you should give proper examples. You should create that curiosity in the minds of people. Even at the higher education level, a lot of people are not taught what is the use of this science, how it can be applied to technology. Since he coming and talking about a principle or a concept is not going to help, students will lose interest very fast. I think we'll have to also change the way we teach some of these subjects, the science subjects. Yes, not all subjects, but some of these subjects, for example, physics itself, right? Not many people are coming forward for mathematics. The people who come there, if it is their first choice, I'm extremely happy, but it is not. Just because they have not got any other, this one, they get into BSc, then they don't get jobs. They come to MSc programs. And most of these people, who do not get jobs in industries. The most dangerous thing that happens is, without choice, you come there, you study your MSc, and then finally you get into teaching line. Whether it is at PU level or whatever level you get into, you are harming the entire, ecosystem itself. That should not happen. I think we are also at fault as administrators, as policymakers, including the government, right? Randomly, allowing 500, 600 engineering colleges across the state, right? Is not the right way of moving forward. That means it's a lopsided development. Engineering is important, technology is important, but the science behind all this, if you don't understand, if you're not able to understand, not possible. And also as I told you, the mindset now. Not many people are interested. They start looking at salaries. So if you have just got a BSc and MSc, some people feel that they do not get the right kind of salaries what an engineer gets. It's a very wrong concept. If you go outside the country, right, and even in this particular country, right, people who have got the core competence in science, they are paid very heavily. Right? You go to biotech, like, Biocon, that is a very flourishing company today, available, like, located in Bangalore. You see, most of them are all scientists, and they're all paid very well. It only things that you have to develop core competence. So the whole idea of, like, having this particular conference, the symposium for 2 days, is to create an awareness among, like, the students and participants about the emerging, like, trends in advanced materials, and also how it can be applied, how it can be used, how new technologies can be built. I'm also very happy that the Department of Chemistry, Physics, Mechanical, and Polymer Science, all these people are doing very good, like, research, even in the university, in terms of, like, advanced materials, right? So there's so much of, like, things which have developed. We have got smart technologies today, smart, that is possible only because of smart materials, nanoscience, nanotechnology. I think we are going to discuss some of all the, like, this. I once again congratulate the department, and I'm sure these 2 days will be definitely, like, useful for all the participants. Make the best use of it, and let it be very fruitful for each one of you. Thanks for, like, being here, and I should also thank our chief guest, Mr. Vedi, for our very inaugural, like, lecture. Thank you.
Thank you, sir, for your insightful presidential remarks at this event. Now I request Professor Mohan, sir, from the Department of Physics to deliver the vote of thanks.
Thank you, Amrita. Taking the divine blessings of His Holiness Dr. Shivatri Rajendra Mahaswami Garu, and going to the lotus feet of Dr. Shivatri Keshikendra Mahaswami Garu. It's my privilege to deliver a vote of thanks in this august gathering. First of all, I'd like to thank our chief guest, our beloved teacher, Professor S. Krishnamani Madam, for kindly accepting our invitation and to be the chief guest. And also, she's kind enough to give an invited talk with her. Thank you, ma'am. Actually, I was in the first batch which you handled in Gangotri, ma'am. Thank you very much. And also, I'd like to thank our Honorable Vice Chancellor, Professor A. Santosh Kumar, who motivated our physics department to conduct this workshop, symposium, and also gave the continuous support, refining all the structure and framework of the symposium, and for his continuous encouragement. Sir, wholeheartedly thank you. Also, I'd like to thank our beloved principal, Dr. C. Nataraju, sir, for his continuous support in organizing this event. Also, I'd like to thank our Dean Science, Dr. P. Maloo, sir, for his continuous encouragement and support. Also, I would like to thank all the deans, Dean IQAC and QALA cell, also all the HODs of various departments for their kind support and encouragement. Thank you. I would like to thank all the faculty of various departments for their kind support, continuous encouragement. Thank you. And also, I would like to thank all the teaching staff of physics department, our beloved convener, Dr. Madhusri, for organizing this beautiful occasion, symposium. Thank you, sir. I'd like to thank all the faculty of the physics department and also the non-teaching faculty of physics department for their tireless efforts and continuous support to organize this event, 2-day symposium. Thank you, last but not the least, I would like to thank all the registered participants and all the young researchers who are going to present their work in this symposium. Thank you. Finally, I would like to thank one and all who have supported us, encouraged us, gave their continuous support to organize this event. If I have missed their name, thank you. Thank you very much. I would also like to thank our registrar, sir, Professor S. Dhanraj, sir, in his absence here. Sorry for our forward. Thank you. Registered participants, please be seated.
ಅದು ಇದನ್ನ ಲೋಡ್ ಮಾಡಿಸ್ಕೊಂಡು
ಸರ್ ತೆಗಿಬೇಕಲ್ಲ
ಆ ಟೇಬಲ್ ಹಂಗೆ ಇರಲ್ಲ ಸೇರ್ಸಲ್ಲ
ಅಲ್ಲ ಈಗ ಮೇಡಮ್ ತೆಗಿಬೇಕಾ
ಅದನ್ನ ಲೋಡ್ ಮಾಡ್ಕೊಂಡು ವಿಡಿಯೋ ಮತ್ತೆ ಪ್ರೆಸೆಂಟೇಷನ್ ಇದೆ ಮೇಡಮ್
ಅದು ಅವ್ರ ಲ್ಯಾಪ್ಟಾಪ್ ಅಲ್ಲ
ನಂದು ಅಟ್లా
ನಂದು ಕನೆಕ್ಟ್ ಆಗಿಲ್ಲ ಅಲ್ಲಿ ಇದೆಯಲ್ಲ ಮೇಲ್ಗಡೆ ಅದು ಚೇರ್ಸು ಮತ್ತು ಟೇಬಲ್ ಎರಡು ತೆಗಿಬೇಕು ಫುಲ್ಲು ಓಪನ್ ಬಿಡಿ ಮುಗಿತೀನಿ ಯಾರು ಬರ್ತಾರೆ
ಒಬ್ಬರ ಕೈಲಿ ಆಗಲ್ಲ ಟೇಬಲ್ ಭಾಳ
Dear participants, who are not yet registered for this event, you can no way. It's open after the meeting. Now you just go to the but later you can complete the registration.
ಅದು ಹಿಂದೆ ಹಾಕ್ಬೇಕು ಓಡ್ತಾನೆ ಹಿಂದೆ ಆನ್ ಮಾಡು
Good morning, one and all. So let me start my presentation. I'm going to speak on surface engineering to enhance the efficiency of triboelectric nanogenerators for sustainable energy harvesting. So we have already seen our main research topic, whatever the symposium topic is, sustainable energy materials. So that's why I have chosen this particular topic. The outline of my presentation goes like this. So nanogenerators, I'm going to define what are nanogenerators and what are particularly triboelectric nanogenerators. We have done 5 works, so I'm going to briefly explain these 5 different works. RGO nanocomposites base 10, PVA graphite base 10, PVA multi-walled carbon nanotubes base 10, nickel ferrite nanoparticle base 10, and copper selenide nanoparticle base 10. And all these work have been already published and also followed by the conclusion. So let me define what are nanogenerators. The nanogenerators are the devices which convert mechanical, thermal, or other forms of small scale energy into electrical energy. Nano is nothing to do with the nanoparticles. Here, nanogenerators means conversion of the small scale energy into electrical energy. So that's why it's called as nanogenerator. There are 3 different types of nanogenerators: piezo nanogenerator, pyro, and triboelectric nanogenerator. So let me tell you what are the different types of nanogenerators. The first one is piezoelectric nanogenerator. So almost all the nanogenerators is put forward or proposed by Wang Group. So this is also piezoelectric nanogenerator is also proposed by Wang in 2006. And these are the devices which convert mechanical pressure into electrical energy through piezoelectric effect. And what is a piezoelectric effect? It is the ability of certain materials to generate an electric charge in response to applied mechanical stress. And next is a pyroelectric nanogenerator. These are also introduced by Wang in 2012. And these are the devices which convert thermal fluctuations, heat energy or thermal variations and thermal fluctuations into electricity via pyroelectric effect. And what is the pyroelectric effect? This phenomenon occurs in materials that have a natural non-echo centrosymmetric crystal structure where a spontaneous electric polarization exists. So because of that effect, there will be a conversion of thermal fluctuation into electrical energy. So next one is a triboelectric nanogenerators, which are our working area. So triboelectric nanogenerators, we usually call them as tanks. So TENX was introduced by Wang in 2012. You can see that it's a very budding research field. So it started in 2012. And if you go to the literature, you can see lots of papers are coming in this particular field. And these are the devices which converts mechanical or vibrational energy into electricity by the phenomenon of triboelectrification and electrostatic induction. So what is triboelectrification? Triboelectrification is the process which we usually experience in our day-to-day life. That is the process where materials become electrically charged through friction, contact, or separation. And the charges are going to be flown by the process of electrostatic induction. It is the redistribution of electric charges within the material due to the presence of a nearby electric field. This is the redistribution of electric charges. So usually triboelectric nanogenerators works on the 2 models. The first model is a dielectric model. In this model, so you can see that there are 2 dielectric materials of opposite polarity which are attached to the metals. Okay, so in order to generate the charges. And the second model is a dielectric metal model where you will have only one layer of dielectric material which is going to be paired with the metal. And these different tank models have a different applications. In the dielectric model, we get high efficiency of energy harvesting. That is going to be useful in wearable devices. And in the dielectric metal model, it will have a simple design for sensors, which has applications in sensors, and also in a basic energy harvesting systems. And of course, each model's efficiency is based on the choice of the material and its properties like surface area and also the dynamics in which the motion of the two layers are going to be made. So we cannot say which model is highly suitable. It depends upon the choice of these parameters. So what are the applications of the TENS? So if you see the applications, it has a vast applications, mainly in like sensing mechanical motions, and also we will have applications in a wearable devices, optical scanning, tunable grating, plasma display, and also in electroadhesion, electrospinning. I think you can find a vast field of applications for these triboelectric nanogenerators. So let me tell you what are the fundamental modes of TENS, which till today people have not understood properly the mechanism of triboelectric nanogeneration. They have just predicted some modes. Okay, so 4 modes of working of these triboelectric nanogenerators. Still work are going on. Theoretically, there is no proper understanding. So we can actually make our TEN device, that's a triboelectric nanogenerator, in 4 different modes. The first one is the vertical contact separation mode, in which, so I told you already, we'll have 2 layers which is attached to the electrodes. So there will be vertical contact between the layers. There will be a upper layer coming and contacting the lower layer. So when it touches and separates, there will be flow of charges. And the second one is lateral sliding mode, in which one layer is going to laterally slide over the bottom layer, upper layer is going to be slided over the bottom layer. And we will have a single electrode mode. So in single electrode mode, you will have only one electrode and one TEN layer. So that is called single electrode mode. And also we'll have a freestanding triboelectric layer mode, in which we will have a 2 TEN layers on which one TEN layer is going to create a friction. So we can slide over this upper layer on the 2 layers. So these are the different 4 modes of triboelectric nanogenerators. So the next question is why we are motivated to take up this particular work. What is our motivation behind this research on nanogenerators? So all of you know there is a rising demand for sustainable and renewable energy sources. So because we have a dearth for the renewable energy sources, so we have to find out the alternative resources for the renewable energy sources. So therefore, we are actually finding alternative sources of generating energies. So obviously, nanogenerators or the triboelectric nanogenerators are one of the choice for that. And these triboelectric nanogenerators have potential for self-powered, wearable, and portable electronics. So I don't say you can, satisfy the need of a house or something like that. So by using triboelectric nanogenerators, I cannot generate a power of mega scale or the macroscopic scale, but by generating the power at a nanoscale also, we can use them as a self-powered wearable and portable electronics application. And also they are going to be very good in healthcare applications and also environmental monitoring, and particularly in IoTs, Internet of Things, and also advancements in nanotechnology. So if we incorporate certain nanoparticles, so that is also going to increase the high efficiency of the triboelectric nanogenerators. So mainly these are all the motivations for taking up our research. So the next question is, what are the type of materials which we can use for fabricating the triboelectric nanogenerators? So usually we should select 2 types of materials. One layer should be tribopositive and another one will be tribonegative, apart from the electrodes. So coming to the tribopositive materials, these materials are going to lose ions or electrons and become positively charged when in contact with other materials. And the tribonegative materials are the materials which tend to gain electrons and become negatively charged. One should give away the charges and another material should take away those charges. And if you see, this is from the literature, you can see you have a series of tribonegative materials, and also it has been listed a series of tribopositive materials. So tribonegativity increases this way and tribopositivity increases this way. So you have to choose, depending upon the literature, what is the suitable combination of negative and positive layer. And it is not only that factor makes efficient device, rather other properties of the materials are also going to decide about the pair of the device, a pair of the layers which we are going to choose. So these days we have some advanced and sustainable materials which are not mentioned here can also be used. So like biodegradable materials, for example, cellulose, gelatin, chitosan, silk fibrine, etc. And also we can convert the waste materials into a usable form. So recycle, they are called recycled materials. For example, waste plastics, used fabrics, rubber from old tires. All these materials can be converted into useful triboelectric layers. So now next question is, so we can choose the material from this series, no doubt. So you can choose any of the material from this series and you can form a tank layer. But that is not going to be a good tank. Okay, that is not going to be a good triboelectric nano generator because that may not generate, higher efficiency, voltage or current. So then what are the strategies in increasing the efficiency for triboelectric nano generators? So the main strategies are either we can increase the, surface charge density through the physical modification techniques or through chemical modification techniques. Because if we increase the surface charge density, charge holding capacity of the triboelectric nano generator is going to be high. So if we increase the surface charge density, there will be a generation of more charges, and if we generate more charges, more current will be generated, more current in the voltage will be generated. So in the physical modification techniques, we will have mold imprinting, nanomaterials which are associated with the surface modification. We can blend the nanoparticles with the tank layers and we can increase. And also we can choose the materials which have porous surface structures. So that is also going to increase the whole charge holding capacity of the material. So in the chemical modification techniques, so these are usually the methods: corona charging, ion injection, base treatment, plasma treatment. So you will have many more methods. So we have listed only a few techniques here. So let me come to our work. So as I told, I am going to explain now five of our research papers briefly. So the first one is synergetic effects of RGO functionalized, reduced graphene oxide functionalization in nanocomposite based triboelectric nanogenerators for enhanced energy harvesting. This paper has been published in 2024 in Sensors and Actuators A. So why we have chosen RGO? Because RGO, functionalized RGO. It's not a plain RGO, it's a functionalized. So we have functionalized it with the OH group and also with the COOH group and also with the NH2 group. So this is a graphical abstract of this particular work. So you can see this is a fabricated tank device and you can see the functionalized group structure here, PVA, OH and RGO. Okay, so PVA with the functionalization with the RGO. So you can see that the voltage is going to be increased as we change the functional groups. This is for the plain PVA. This is for the PVA with the functionalized RGO with OH group. And this is for the COH group and this is for the NH2 group. So similarly, you can see that the current is also going to increase. Okay, so functionalization itself is the chemical way of increasing the surface charge density of this tank. So here it's a very, very simple fabrication. So as I told, functionalized RGO enhances tribopositivity. Tribopositivity increases the output of the tank device. And also we can see here that RGO functional groups will certainly impact on the triboelectric performance. It is evident from these particular graphs. So sample preparation is very simple. So here we have taken DI water at 60 degrees Celsius and then 7 grams of PVA is going to be added on a hard plate with a magnetic stirrer. And after that, we are going to add functionalized RGO, then transfer that solution into the Petri dish and then peel it off. So this layer is going to be ready. And after that, in order to fabricate the device, so we are going to take a PET as a substrate, aluminum as an electrode, PP layer as another layer, and PP as a tribo negative layer. So here you can see that in this second layer, you will have a functionalized graphene oxide, and this is going to be the device after fabrication, and this is the real picture of the device, real-time picture of the device. So after fabricating the device, so the device has been subjected to the different characterization. So we can see here we have performed XRD, EDS, SEM and FTIR. So you all know that XRD is going to indicate whether there is a formation of the functional groups or not. So the bottom figure is for the plain PVA and the second is only for the functionalized RGO, and then you can see PVA plus 2% of OH functionalized RGO and then COH RGO with the function with PVA and the plain one and with the PVA. And you can see that there are prominent peaks which indicate the functional group, presence of the functional groups. And we have taken the EDS spectrum for knowing chemical composition, percentage, weight percentage of the, whatever the elements present in that particular layers. And here you can see that in the same image, in the pristine PVA, you can see that there are no, appearance of the, what I can say, roughness on the film. But when it is included PVA plus 2% OH RGO, so you can see that there are rod-like structures which are appearing. And also here you can see in the third figure with the 2% COOH, you can see some uneven structure which is visible, and also with the NH2 there is a more agglomerated like structures are appearing in the same image. And with the FTIR you can identify the presence of functionalized groups, and also what are the different what I can say contribution of the functional groups, that can also we can understand. And after the SEM, so we have also taken the AFM spectra. So AFM figure actually show more accuracy about the surface roughness. And also we have taken KPFM also, so that is also going to indicate the depth or in-depth picture of the surface roughness. And also it is going to show more three-dimensional high resolution picture of surface. So these characterizations, so we have done the electrical characterization. So out of all the devices, all the functional groups, what are the different functional groups? We have NH2, COOH and OH. So we have come to know that NH2 functionalized graphene oxide triboelectric nanogenerator showed maximum voltage, and the voltage was observed to be 322.46 volts. So this is the AC voltage, okay? So don't think it's a DC voltage. And also the current of 78.22 microamps. So we have optimized this device and we have used it for further application. So we have not taken the other functionalized group. So so the device actually generated a peak power of 2.83 milliwatt at 50 mega ohm. So this is the device, and these are the open circuit voltage and the short circuit current of the different functionalized group tanks. And you can see that here we have also checked the performance of the device with the force applied and also with the size. So you can see that as force increases, force means the tapping force of the device. Okay, so we have to tap the device from the top surface. So if we increase the force, the output is going to be increased. Okay, so and also here you can see that as we increase the size of the device, okay, so you are going to provide more surface area. So as surface area increases, the voltage is going to be increased. And also here we have plotted voltage and current as a function of load resistance in order to find out the power. So here you can see the maximum power, which is generated to be 2.83 milliwatt at 50 mega ohm. So what are the applications? So how far these triboelectric nanogenerators which have been constructed using functionalized reduced graphene oxide are useful. So this device, so along with the rectifier, you can see that we have taken the output through a rectifier in order to convert AC to DC. So we can see that it can power 35 LEDs. So it can power 35 LEDs, and also it can power wristwatch. Okay, so this is off, but when we tap, it will be on. It can power wristwatch, and also here you can see that. So the whatever the triboelectric nanogenerator we have constructed is stable up to 10,000 cycles. So it's physically stable up to 10,000 cycles, and also it can charge the capacitors of 1 and 2.2 micro farads to 3.6 and 3.3 volts. Okay, so that is the maximum voltage that these capacitors can sustain. Okay, so let us move to the next work. That is about the first work. So in the second work, so we have studied what are the annealing effects on the performance of PVA graphite based triboelectric nano generator. This paper has been published in Sensors and Actuators in 2024. So why we have chosen graphite? Okay, so earlier it was reduced graphene oxide, but here it is graphite because graphite enhances surface roughness. So this is according to the literature, and graphite facilitates efficient charge transfer. So that is another motivation. And also we wanted to check what is the impact of annealing. Okay, so when we heat up the tank devices, how does the tank is going to respond? Okay, so impact of annealing on the tank output. So that we wanted to check. And this is a graphical abstract. So you can see here that we have, PVA with graphite is going to be put on a hard plate. It's going to be annealed, and then the tank device is going to be fabricated. And then here you can see that. So this is a TGA graph. So you can see that for plain PVA graphite 50. So as temperature increases, its weight percent is going to be decreased when we are going to anneal it to 80 degrees Celsius. And also you can see that if you take the voltage, okay, so as we go on annealing up to 80 degrees Celsius, it improves the performance of the tank device. So sample preparation is very simple. So the same procedure as I explained. Okay, so we'll take a DI water at 70 degrees Celsius, add PVA and then 0.4 gram of graphite, and you will have a composite, put it on a petri dish and then dry it and peel it off. And what we will do is we'll put it on a hard plate and you anneal it to a different temperature, and you will have a top layer. The top layer will be you will have a PP layer, and the bottom layer you will have a annealed graphite PVA. Okay, so this is the final fabricated device. Okay, so as usual, we have taken XRD, SEM and EDS spectra, analysis for this. So we can see that for the XRD, this is a plain PVA and this is the plain graphite, and this is with the PVA and graphite. That indicates the formation of both, coexistence of both the PVA and graphite. And then this is a XRD for PVA graphite at 50 degrees Celsius, and this is for the PVA graphite at 80 degrees Celsius. So you can see that the graphite peak is going to become more intense as we are going to heat it or anneal it for 80 degrees Celsius. So you can see that for the plain PVA, less of surface roughness is visible, and when we add PVA graphite, that's going to be enhanced. But as we go on heating it, there is a modification on the surface structure of the PVA graphite with 80 degrees Celsius annealing. And as usual, EDS will show the chemical composition of these layers. And also we have performed FTIR, TGI and DTG. So the same is going to be evidence from these things. And also you can see here that from the TGA spectrum, so weight percent is going to be reduced when we anneal it for 80 degrees Celsius, and it is also evident from the DTG plot. Yeah, so after this surface characterization, so we have performed electrical characterization for these devices. So as I told, since 80 degrees Celsius annealed the device showing a better performance, that is evident here. Okay, so you can see here. So here, the black one is a PVA, red one is a PVA with graphite, and blue one is a PVA graphite annealed at 50 degrees Celsius, and pink one is for the PVA graphite annealed for 80 degrees Celsius. So you can see that the voltage and the current is going to be, maximum for this. So the device showed maximum voltage and current of 200 volts and 12.68 microamps for this 80 degree Celsius anneal. And also the device generated a peak power of 4.5 milliwatt at 50 mega ohm. So here also we have checked the performance of the device voltage with the increasing force. And also here we have plotted voltage in the current with the as a function of load resistance, and we have calculated, and also we have seen the stability of the device. So what are the applications? We have simple applications in this particular thing also. The device is charged 2.2, 3.3 and 4.7 microfarad capacitors which are commercially available to their optimum voltage, and the device can power 43 LEDs in series. So that is evident here. So I have also videos, if you want I will show it in the last. So that can also power a watch. Okay, so with the rectifier, okay, so this is a circuit for powering LEDs as well as the watch as well as the calculator. Okay, so they are the applications. And yeah, so let's move on to the next work, that is PVA multi-watt carbon nanotubes based triboelectric energy harvesting device. So this work is published in Surfaces and Interfaces in 2024. So multi-volt carbon nanotubes actually enhance the performance of triboelectric nanogenerators by increasing the contact area and also boosting the charge generation. That is our main motivation. And also this addition of multi-wall carbon nanotubes into the PVA increases crystallinity of the layer, and also it increases the mechanical strength. So that is a major motivation behind choosing this particular. So here you can see the graphical abstract. So we have, this is how the device looks, and it works on the hand tapping, and the signals are going to be generated. It could generate 542 microwatt of power, and this is actually used as a smart door controller. Okay, so this is having a particular application as a smart door controller. So the sample preparation is simple. In this particular work, the sample preparation is as usual as I explained in the last work. Here we have used a waste plastic bottle. Okay, so for the layer of a triboelectric layer. So we have cut this bottle, a portion of this bottle, and we have used it as a triboelectric layer. And this is the PVA multi-wall carbon nanotubes layer. And when we complete the fabrication, the device looks like this. So the real pictures of the device looks like this. The final structure is like this. It is an arc structure. Arc structure actually facilitates maximum contact between the two layers. So the XRD, SEM, EDS and FTIR spectra for these layers. So that will confirm, this is for the plain multi-wall carbon nanotubes, and this is for the PVA, and then with the 0.0258% and 1.68%. So you can see the confirmation of the formation of these, both PVA as well as the multi-wall carbon nanotube. So you can see here, these are the SEM images. This is for the, PVA, plain PVA. And when we add up these multi-wall carbon nanotubes, a different percentage and different resolution, you can see there is a, creation, or there is a formation of what I can say uneven surface. Okay, so that is, you can see a sponge-like structure which is helpful in, holding the charges and transferring the charges from one layer to the another layer. And also we can confirm the same thing. Okay, so this EDS will give us the material composition, and in the FTIR we can trace out the formation of the functional groups, so whether these carbon nanotubes are present or not. So that is going to be confirmed. So again, the next step is to check the electrical output performance. So here we can see that the multi-wall carbon nanotube stem generated highest output voltage. So here we have plotted for different concentration of MWCNTs. So you can see that it is going to be highest, and the voltage generated is 340.87 volts at a current of 7.04 microamps at 1.68%. Okay, so after that, we cannot include more percentage of multi-wall carbon nanotubes, as it creates increases the surface, what I can say, rigidity of the film. And also the maximum power generated by the device was found to be 542 microwatts. And the rest of the things are explaining stability of the device, and also to calculate the power, and also you can see the usual trend of 10s that is increase in the output voltage with increasing in the force. So coming to the applications, the device could store the energy of 17, and it can charge 2.2, 3.3, 4.7 and 10 microfarad capacities respectively, so which are commercially available. And also it can power 82 LEDs, so that is shown here. And also it is functioned as a smart door, self-powered smart door. If some, there will be a tank attached to the mat. Okay, so in front of the door. Suppose if anybody just puts their leg on that, so it will be counted as a one person. Okay, so it is going to be act as a self-powered smart door, and the door is open. Okay, so it will be closed if somebody goes and taps on that, so the door is going to be open. So this is going to work as a self-powered smart door. And this is the fourth work. So that is spinach mediated green synthesized nickel ferrite nanoparticle based triboelectric nanogenerator. So this work has been published in ACS Applied Electronic Materials in 2023, it says. So so why we have chosen nickel ferrite nanoparticles? I told one of the way to increase charge density, okay, surface charge density of the triboelectric nanogenerators is adding suitable nanoparticles. So these nickel ferrite nanoparticles synthesis is through green method, and synthesis is cost effective and sustainable. So we are not going to use any harsh chemicals, and also we are not going to use any tedious method of synthesis of nanoparticles. And also it promotes the formation of porous and porous structure on the layer, tail layer, and also in that way it improves the surface roughness of the device. So you can see it forms the honeycomb structure. So this is a graphical abstract, and it can also act as a biomechanical sensor. So you can see plain PVC. So here we have used a PVC, not a PVA. And these are the different weight percent of the nickel ferrite nanoparticles. So you can see that 0.6, weight percent of or gram of nickel ferrite nanoparticle gives the highest voltage and current. And also this addition of nickel ferrite nanoparticles increases dielectric properties of the device. So increased dielectric properties is a favorable condition for the triboelectric nanogenerators, and it enhances the device ability to absorb water molecule. It is hydrophobic, and it enables humidity and temperature sensing capability. So this device can also act as a humidity sensor and also the temperature sensor. So they are the major motivation. Okay, so in order to fabricate a device, we should have a certain motivation. Otherwise, it is not going to be like publishable. So nickel ferrite nanoparticle synthesis is through the green synthesis, that is by mixing nickel nitrate and ferrous nitrate with the Malabar spinach, an extract of the spinach leaves, and then stirring for the 2 hours with 400 RPM. And it is going to be subjected to calcination for 3 hours at 500 degrees Celsius. And there will be formation. After that, there will be a formation of nickel ferrite nanoparticles, the same images of which is shown here. Okay, so after the formation of the preparation of nanoparticles, so we have to prepare the layer, right? So triboelectric layers. So for that, the usual solution casting method is used, and after that, the usual procedure is followed for forming the tank. So this is a real picture of the tank, and this is a pictorial representation of the tank. This is also formed in a arch shape. So after the formation or after the fabrication, we have to confirm the formation of the device through XRD, SEM, FTIR, and UV. So XRD actually indicates the crystallinity of nanoparticles. So you can see that after we add NiFe2O4, so the crystallinity of the device is increased. And also these are the SEM images which can show the surface roughness. So you can see the agglomerated nanoparticles with the particle size which ranges from roughly 32 to 44 nanometer. And also FTIR analysis indicates the formation and the presence of the functional groups. And UV visible spectra actually indicates there is a charge transfer transition from O2 minus to Fe3 plus, which is present at 277 nanometer. And at the 237, this peak indicates the electron transition from valence band to the conduction band. And at this 376 nanometer, so it indicates the surface defects are the impurities. And also we can, calculate what's the energy gap by using this data, and it is found to be 5.15 electron volt. Okay, so you know that the more than 5 electron volt material is going to be insulator, right? So basically triboelectric nanogenerators are insulators. And here you can see that this is for the plain NiFe2O4, and the same has been repeated for the PVC NiFe2O4 composite film. So we can see that confirmation of the formation of the composite, and also you can see there is a honeycomb-like structure when we combine PVC with NiFe2O4. That is going to increase the charge holding capacity of the entire device. This is the ADS, and this is going to, we have also measured dielectric constant. So we can see that dielectric constant is going to be increased as we increase the weight percent of the nickel ferrite nanoparticles. Yeah. So when we measured electrical performance of the device, PVS NIF10, so we can see that the device attained the maximum voltage at 0.6 grams. So this is evident in this particular figure. So it can generate 66.09 volts and 6.33 microamps. You can see that it's not a very big voltage which we have generated here. And also the current is higher for that. And after that, we have also calculated what are the transfer charges as a function of frequency. And also we have measured what is the power, maximum power that the device can give. It can generate 256 microwatt at a load resistance of 40 megaohms. And also we have seen the stability. Okay, so what is a stability of the rectified voltage? It could be stable up to 6,000 cycles. Okay, and that is also checked for the open circuit for different layers. So what are the applications? Coming to the applications, so as I told you already, so we have checked this device with different humidity. So relative humidity, RH is relative humidity. The device output decreased with the increase in relative humidity. That means it is not humid resistant. It's going to change its output with the humidity. So we can use it as a sensor, humidity sensor. And also the output increase with the increase in temperature. So we have also checked with the temperature. So with the temperature, the output increased from, when we increase the temperature from 10 to 40 degrees Celsius, and after that it is decreased. So we can even use it as a temperature sensor. And this device can charge 3 capacitors, and also it can power 15 green LEDs. So you can see the voltage is less in this particular tank, so it cannot charge more LEDs. And also it can be used as a biomechanical sensor. What I mean by that? So it can distinguish or discriminate between different types of motions like jumping, walking, and hand tapping. So you will have it can generate a different frequency for different types of motion. So it can be used as a biomechanical sensor, and also it can be used as a hand tapping buzzer. So if we just touch it, so it can be also act as a tactile sensor. If you touch it, there will be the buzzer will make a sound. So this is also another application. And also it is used as a smart gate controller. Okay, so we have a video, I will show it later, by using Arduino Uno board. So what we have done was there is a gate, and when vehicle comes, and we have placed 10 layers there. When the vehicle crosses or touches or it moves over the 10 layers, so it will give certain signal and the gate will be open. Okay, so as the device crosses, the gate is going to be closed. Okay, so it is used as a smart gate controller. So let's come to the last work, that is the copper selenide as a fissile nanomaterial for tank fabrication. So this has been our recent publication, and it is published in Chemical Engineering Journal, and you all know its impact factor is 13.5. So yeah, what is the motivation behind choosing this particular work? So copper selenide is a wide band gap. It is having a wide band gap, and also it is having a very good dielectric properties which is suitable for our tank fabrication, and it increases the effective contact area. That is another thing, and also it is eco-friendly and mechanically durable. So these are the 3 important points which made us to take up this particular work, and fabricate this device. So this is the graphical abstract. You can see this is the device, and these are the power generated, and it can usually, it can usually power watch and LEDs and other things. Apart from that, we have designed the tank, copper selenide tank for powering a braille keyboard. Okay, so by powering this braille keyboard through Arduino board, so we can make it to generate few words. Okay, so that is a very important application which drawn a high attention. So the sample preparation is as usual through a simple solution casting technique. So it's a very simple thing. So DI water is taken along with 5 gram of NaOH at 80 degrees Celsius. So 0.15 gram of selenium is added, and then it is stirred. After 5 hours, you can see the copper selenide here. So after 1 hour, you can see the formation of the copper selenide particles here. And then we are going to make films out of it by the solution casting technique. So by adding 7 gram of PVA, for 2 hours you have to stir it. And then you will have a PVA copper selenide nanocomposite. Leave it for 20 minutes and then put it on a petri dish and peel it off. You will get a layer. So here also we have used a PET water bottle, which is a waste water bottle, in order to make a arch-like structure. And these are the different layers, and this is the final picture of fabricated thing. So coming to the characterization, so we have performed SEM, TEM, XRD, dielectric, constant measurement, FTIR and UV. So here you can see that the SEM images, you can see there are what I can say fibrous-like structure or rod-like structures. In order to find out what is the dimension of this rod, we have taken the TEM image also, and you can see different images of the SEM. Okay, and also there is a plot of XRD here. Okay, so here you can see that green color indicates PVA and black indicates 0.1% of the copper selenide, red indicates 0.2%, 0.4% and 0.8%. So you can see that as we increase the concentration of the copper selenide, so there is an increase in the intensity of the peaks, which indicates increase in the crystallinity. Okay, so here also it is evident dielectric constant is also going to increase with the increase in the percentage of the copper selenide, and also you can see the functional groups, and also we can see we can calculate what is energy gap by using this UV visible spectroscopy. So coming to the electrical performance, the device with 0.28% copper selenide. So it can only generate up to 0.2%, it can generate high, otherwise the voltage, output voltage is going to be decreased. So we can see that it could generate around 400 volts and 83.45 microamps, and it generated an output power of 67.6 milliwatt. So this is indicating the stability, and this indicates the function, voltage as the function of frequency, voltage as a function of force, and this is a rectifier circuit. And this is to calculate or to study the voltage and current as a function of load resistance, and this is for the calculation of the maximum power delivered. Okay, so yeah, what are the applications I was mentioning you in the beginning? So PV and CU2AC tank can usually, so these are the basic applications of any triboelectric nano generators. So it can power different capacitors and also the LEDs. If 57 LEDs, it can glow, and also a smartwatch. Okay, so this is a circuit for representing the circuit. And as I told you, it can act as a self-powered braille keyboard. So this is actually done by a project student. So here you can see that we could generate letters A, C, O, and semicolon and a slash. And also we have this is a coding design for that, and that we have done by using a Arduino board in a computer. So you can see this, and if you want to know about further information about this work, you can just visit the paper. Okay, so yeah. So these are the 5 important works so we have done in the last 1.5 years. So let me, I cannot tell all the work because we have published around 30 papers in this triboelectric nano generators in the last 2-3 years. So let me conclude my presentation. So what are the main conclusions in all these four work is we are addressing sustainable energy solutions. This actually demonstrates the formation of the tanks and the capability of tanks to convert biomechanical energy into electrical power, an alternative to fossil fuels and the conventional batteries. So still this is in the research level, so it has to be industrialized to a large scale. Okay, so you all know it is started in 2012, and if you see the internet, it is a top 2% research field in the world. Okay, so second one is it highlighted the scalability of the tanks for diverse energy harvesting applications. So we have demonstrated it through different applications, and also advanced the development of renewable energy solutions by showcasing low cost and environmentally friendly trade tank fabrication methods. We have adopted the simple methods. We have adapted the materials which are locally available, and also what I can say, waste material. So that is also one of the thing. And also there is a environmental conservation in this particular idea. So it reduced dependency on virgin resources by recycling materials to functional devices, minimizing environmental degradation. So in our other type of work, we have used all the waste materials also to convert into tank. And it's contributed to carbon footprint reduction by promoting energy efficient manufacturing processes and waste utilization. And it supported global sustainability goals by addressing waste management challenges through innovative eco-friendly solutions. And finally, we have demonstrated it for practical applications. We have not just put forward our idea, but we have used the tanks for charging capacitors, powering LEDs, driving wearable sensors, and which showcases their versatility. And we have demonstrated the feasibility of self-powered biomechanical sensor for healthcare monitoring and environmental sensing. And they highlighted the potential for tanks in the off-grid energy systems and low-power Internet of Things applications. So these are our some of the publications in this particular field. So yeah, this is my research group. So this is a first student who have worked in a 10 group, and she is a postdoctoral fellow, and she has done PhD in 10 group. And these two, Amini and Adarsh, are working in the 10. And these are my collaborators, Dr. Sangamesh from NIE and Madhukar from JC. Thank you. If you have any questions, please open for discussion. Any questions? No? So if you have any questions, you please ask me. I will be very happy to take up. No?
So I think few of them are doing on.
Henga?
Chemistry,
Chemistry, Yashaswini, I can see. Yeah, we have collaboration with the chemistry.
So no questions.
No questions means either you have understood everything or nothing. Nothing is the correct thing, I think. Okay, thank you. Thank you for your attention.
Thank you, ma'am, for your insightful words about triboelectric nanogeneration. Now I request Dr. Madhusri